Okay. I'm still not ready. I have to share the screen. So constant rule, derivative of a constant is 0. That comes from last week. These all come from the derivative rules. The derivative of a constant times a function is a constant times the derivative of a function. The derivative of two functions added or subtracted is take their derivatives separately, add them and subtract them. So then we're going to talk about the power rule. So this is what's the derivative of something to a power, x to a power, x squared, x to the negative 10, x to the 1/5. What's the derivative of something to a power? So I'm going to start with x squared. And when you draw x squared, you get a function that looks like this. On the left-hand side of this parabola, what kind of number will the derivative be? A negative number, because this is going down. On the right-hand side of this parabola, what kind of number will the derivative be? Positive number, because it's going up, right? Right here at 0, the bottom of the parabola, what do you expect the derivative to be? 0, yeah? Is this derivative over here going to be a big negative number or a small negative number? Big. So it starts at big negative numbers, gets closer and closer to 0, then goes back up to big positive numbers. The derivative of this function looks a lot like this. So the derivative of a quadratic, x squared, looks a lot like a linear function, which has a power of x. It turns out it's 2x. The slope of the line that you get there is 2. If you did the derivative rules, the definition of the derivative for x squared, you'd end up with 2x. So if we sort of extrapolate from there on how we do the derivative of something to a power, we put that power in front and make our exponent 1 smaller than it was before. And this rule works for any powers of x. It works when x is positive, or for any powers of n, any values of n. It works when n is positive, it works when n is negative, it works when n's a fraction, it works when n's a decimal, it works for any values of n. Okay, this power rule works for any values of n. Okay, so let's do an example. This guy says, find the derivative of the following function. So what we know from our list of rules up at the top is if I want to find the derivative of all of these things added or subtracted together, I can just find the derivative of each piece separately, right? And if I want to find the derivative of something like 3 times x to the 7th, I can just do 3 times the derivative of x to the 7th. So if I want to find the derivative of this guy, I'm going to go slowly at first, and then as we practice more, we'll go faster. I'm going to do 3 times the derivative of x to the 7th, minus 4 times the derivative of x to the 5th, minus 1/3 times the derivative of x cubed, plus the derivative of x squared, minus 3 times the derivative of x, plus the derivative of 7. Okay, so almost all of these use the power rule, right? X to the 7th uses the power rule, x to the 5th uses the power rule, x to the 3rd uses the power rule, x squared uses the power rule. How about 7? Does it use the power rule? I mean, it could. What's the power of x on 7? 0. So you could put that 0 in the front, right? And when 0 is in the front, it's going to turn out to be 0. How about x? Does it use the power rule? Technically, you could, right? This is x to the 1st. So if you take the derivative of x to the 1st, if you take the derivative of a straight line, you're just going to get the slope. So the derivative of x will be 1. You might want to add that to your list of rules. You don't have to, but you can. Think of it as the derivative of mx is just going to be m. Because mx is a straight line with a slope of m. The derivative tells you the slope. So the derivative of something times x is just going to be that something. Just that slope there, okay? Okay, so derivative of x to the 7th. Bring the power in front, 7, x to the 7 minus 1. Derivative of x to the 5th. Bring the power in front, 5, x to the 5 minus 1. Derivative of x cubed. Bring the power in front, 3, x to the 3 minus 1. Derivative of x squared. Bring the power in front, 2, x to the 2 minus 1. Derivative of x, the slope of that line is just 1, plus 0. Okay, so I told you I was going to go kind of slowly to start with, and then as we do it, we won't write so much. Like in practice, I don't write 7 minus 1. I just write 6. Right? In practice, I don't write this 0 at the end. But when you're first starting, when you need to practice, go slow and write those pieces. Okay, 7 times 3 makes 21, x to the 6th, minus 4 times 5 makes 20, x to the 4th, minus 1/3 times 3 makes 1, x squared, plus 2x minus 3. So that's my derivative.
Using the definition.
That would have been, could you imagine trying to do like something to the 7th with the definition? That'd be so awful, wouldn't it? X plus h to the 7th. So miserable. Okay, so sometimes what happens is the function that we're looking at doesn't really fit into any of our rules, right? Like we really only know one rule. We know the power rule. If the function doesn't look like x to a power, we have to do some algebra before we can use any derivative rules. So here's where I want you to be very cautious and very careful and very diligent. Don't ever mix the algebra of rewriting a function and taking the derivative in the same step. So what I always say to do is take one step, rewrite every piece of your function so that you can take its derivative. So it looks like something to a power. Then in the following step, do all the derivatives. Don't do piece by piece, because if you try to do piece by piece, you're going to be like, oh, did I take the derivative of this already? I don't know. And then you're going to take the derivative again, and then it's going to be wrong, right? So be very diligent, very careful. Take a second, rewrite every term so that it looks like something to a power. Then apply those derivative rules. Okay, so let's try it. Oh, I'm not doing any calculus right now. I'm just doing some algebra to rewrite the terms. Can you rewrite x cube root of x to the 7th as x to some power? Yeah, x to the 7 divided by 3. Cube root is like 1/3. So x to the 7th, cube root of x to the 7th is going to look like x to the 7 divided by 3. Okay, minus. How about square root of x? Can you write square root of x as x to some power? Yeah, x to the 1/2. Good job. Plus that 2 just gets to stick there, right? He's just a constant. X to the 5th root of x squared. 2/5. Great. So notice at that step, I didn't take any derivatives. I just took each piece of the function and made sure it looked like something that was in one of my rules. Now what I'm going to do is take the derivative of each piece. I'm going to use the power rule. And I'm going to use that constant multiple rule, which lets that 2 just stick in the front there, okay? So y prime is, bring the power in front, subtract 1 from the power, minus, bring the power in front, 1/2, subtract 1 from the power, plus 2 times, that 2 just sticks in the front, bring the power in front, 2/5, subtract 1 from the power. If you are not good at fraction addition, then you should make sure your calculator is. And you should put this in your calculator. 7/3 minus 1 gives me . What do you get when you do 7/3 minus 1? 4/3. Okay, minus 1/2. 1/2 minus 1 gives me negative 1/2. Great. Okay, in this one, I'm going to do 2 times 2/5. What do you get when you do 2 times 2/5? 4/5. And then 2/5 minus 1, negative 3/5. It is perfectly acceptable for you to leave your answer just like this. You do not need to do any more simplification than that. There's a lot of simplification you could do, right? What does a negative exponent mean? Yeah, it puts it down into the denominator, right? If you have a negative exponent, it sends it down. into the denominator. So we could rewrite this middle term as 1/2, 1/2 is square root. Negative means put it in the denominator. So 1/2 square roots of x. But it's not necessary. You can enter the answer just like this in Infinity and you are going to get it correct. When you take your quizzes on D2L, they're going to look just like this in the answers and you're going to be able to match. When you do your handwritten quiz, you can leave your answer just like this. You do not need to do any simplification. Here's the thing. If you do some crazy simplification because you use some sources that you're not supposed to, I'm going to be like, I don't think you really know that. Yeah. So just leave it just like this. Safest bet. And you might get the simplification wrong. Okay, let's try again. G of x is 1/x plus 4/x squared minus 1/3x squared. I'm going to take 2 steps to rewrite this one because this guy right here, I don't know what to do if I have a whole bunch of stuff squared, right? I only know a rule that says if I have x squared. So I'm going to take 2 steps to rewrite this. I'm going to start by getting rid of that square. I'm going to say G of x is 1/x plus 4/x squared minus 1/, if I square 3x, what do I get?
X squared.
So close. 9, yeah. Yeah, 9x squared. Okay, so all I did was eliminate that square around that big clunky term. Now I want to rewrite this because the power rule says it needs to look like x to a power. It doesn't say that your x to a power gets to be in the denominator, right? The power rule needs x to a power. It needs to be in the numerator. So how can I rewrite this first term so that x is in the numerator? X to the -1. How can I write this term so that x is in the numerator? 4x to the -2. How can I write this term so x is in the numerator? Yeah, the 9 doesn't get to come to the top, right? The 9 doesn't get to come to the top because he doesn't have an exponent on him. He has to stay in the denominator. So when I rewrite this term, the first one is x to the -1. The second one is 4x to the -2. And the third one is 1/9 x to the -2. That third term doesn't get to move to the top. These last 2 terms are common terms, right? Common terms mean they have the same powers of x. If you wanted to, you could squish those 2 together before you take the derivative. How would you squish these 2 together? Yeah, add 4 and -1/9. So do 4 plus -1/9 and see what you get. $35. 35/9. I don't know. Someone has a calculator. I know that 4 is 36/9. -1 makes 35/9. Okay, look, I did 3 steps before I even took a derivative. Right? Like I have not even done any calculus yet. I did 3 steps of algebra before I got to do any calculus. Now I'm going to do some calculus. The derivative of x to the -1 is going to be, bring the power in front, -1. -1 x to the -1 minus 1. Yep. Plus 35/9. That guy just stays there. Bring the power in front, -2 x to the -2 minus 1. Yeah, be careful when you have negatives and you're subtracting. They're going to go more negative, right? So this is -1 x to the -2 minus 70/9 x to the -3. Okay, one more, just to practice the power rule. What you might notice about this guy is that I've got like this huge fraction, right? And I don't know how to do a huge fraction. I don't know anything that talks about, can I just like divide the derivatives? Turns out, no, you can't. So you need to do some algebra to this guy. The algebra that you can do is when you have a fraction where there's only one term in the denominator, you can break this into three separate fractions. What would those three separate fractions look like? Yeah, negative 16x squared divided by 2x plus 5x divided by 2x minus 1 divided by 2x. So my first step is going to be to rewrite this as three separate terms. Yeah, we're going to do that now. Yeah, I'm gonna. Now I'm going to simplify. Okay, negative 16 divided by 2 leaves me with negative 8. X squared divided by x leaves me with x. So I get negative 8x plus. In the second term, I have x's in the top, x's in the bottom. So I'm left with 5/2 minus, this guy's as simple as he can get, 1 over 2x. Can I take the derivative now? What are you going to do to that 1 over 2x? I can't combine because they don't have the same, they have different powers of x, right? 1/2 x to the, what did you say, Adrian? Negative 1. 1/2 x to the negative 1. So that third term I'm going to rewrite as, remember that 2 doesn't get to come up because he doesn't have an exponent. So I'm going to leave him in the denominator, 1/2 x to the negative 1. Okay, so now this is where like the calculus comes in. And this one is, you know, a little bit trickier because they're like, these two aren't really powers of x, right? They are, but they're kind of hiding, right? This third one is easy. Bring the negative 1 in front, subtract 1 from the power. What's the derivative of 5/2? 0. He's a constant. The derivative of a constant is 0. What's the derivative of negative 8x? Negative 8. This is a line with a slope of negative 8. The derivative tells you the slope. The derivative is going to be negative 8. If you want to use the power rule, you can. This is a 1. You bring the 1 in the front, subtract 1 from the power. You're going to get x to the 0. X to the 0 just is 1. So, but we can also just use those rules. Okay, so f prime of x is negative 8 plus 0 minus 1/2 times negative 1x to the negative 1 minus 1. I'm going to do a little bit of simplifying, not a lot. Negative 8, I'm going to get rid of the 0. And I'm going to do negative 1/2 times negative 1 is positive 1/2 x to the negative 2. So really the only simplifying I do when I'm taking derivatives is like multiplying constants together. And it turns out that like the more you practice, you're just going to do this in your head. You're not going to write negative 1/2 times negative 1. You're going to write it as positive 1/2. And you're not going to write negative 1 minus 1. You're going to write it as negative 2. So this step is going to be done like in your head as you practice more derivatives. Okay, so that's the constant rule, the line rule, let's call it, and the power rule. Those three. Okay, here we go. We're going to learn a lot of rules today. There's a sheet at the top of your at the top of this module, module number 4, that has all the rules on it. So we should keep that handy for you. Okay, let's talk about higher order derivatives. What do you think it means if I have like f prime and f double prime and f triple, quadruple prime? That one is, that should be triple though. It's the what? Yeah, it's like the derivative of the derivative, right? So this one is the first derivative. This one is the second derivative, which is the derivative of the first derivative. This one is the third derivative. I took one of those tick marks out. I don't know why I recorded it. So if you've already printed it, take one of those tick marks out. I don't know how, but do it. This is the derivative of the second derivative. So every time you go down a level, you just take another derivative using those same rules that you were using before, okay? All right, this first one's easy because he's already like in the right form. Everybody's ready. We're good to go, right? I'm just going to use power rule, constant rule, yeah? All right, let's do it. So f prime of x is going to be what? 7x to the 6th, bring the power in front, subtract 1 from the power, minus 8x, because I'm going to do 2 times 4, right? I'm bringing the power in front. So I'm doing 2 times 4, 8x to the, what's my new power? 3, plus. In this one, I'm doing 5 times 2. So 10x to the, what's my power? 1. I'm not even going to write that down. Minus, what's the derivative of 3x? 3 plus, what's the derivative of 9? 0. Done. Okay. That's the first derivative. How do I get the second derivative? Do it again. All right. Okay, so I'm doing 7 times 6. 42x to the, what's the new power? 5. Minus 8 times 3. 24x to the, what's the new power? 2. Plus, what's the derivative of 10x? 10. Minus, what's the derivative of 3? 0. Done. Okay, one more. So third derivative, I'm just going to do it one more time. So 5 times 42, 210, x to the 4th, minus 24 times 2, 28, x to the 1, 48, that's better, 48, x to the 1, plus nothing, 0. Okay, so that's the third derivative. Okay, so now it's time for your history lesson. When calculus began, there were 2 dudes fighting over who would win. Newton was one and Leibniz was the other. They each had their own notation. They both have their pros and cons. It turns out that Leibniz won, and he's like considered the father of calculus. One of them uses this notation with the primes. One of them uses this notation with the dy dx, d2y dx squared. This notation, I think the dy dx is really nice because it looks like a slope, right? It looks like a change in y over change in x. So when you're thinking about units, you're thinking the units of y over the units of x. But this is the way we write second derivatives for this Leibniz's notation. But really what this means is dy dx is the same as y prime, same as y double prime. Okay, can I take the derivative of this guy?
Not yet.
Not yet. I should do some work first, right? That first term, that square root of x, doesn't look like x to a power. I can't just take his derivative. So I'm going to do a little bit of work first and rewrite him as x to the 1/2 plus x to the -2. So notice I did not do any calculus yet. I just used some exponent rules. Okay, now I'm going to take the derivative. The derivative of x to the 1/2 is bring the power in front, 1/2 x to the 1/2 minus 1. If you don't know it, put it in your calculator. 1/2 minus 1 is -1/2. Okay. Plus, bring the power in front. So really it's minus 2x to the -3. -2 minus 1 makes -3. Okay, let's try again. I'm going to bring the power in front. So I'm doing 1/2 times -1/2 gives me -1/4 x to the -1/2 minus 1. Put in your calculator if you don't know it. -1/2 minus 1. What was it? 3/2. Good. Okay, now I'm bringing this guy in front. -2 times -3 makes positive 6, x to the -3 minus 1, -4. So remember, the more you practice, the easier this part's going to be, right? If you need to still write down the number, the parentheses, put it in, do the subtracting 1, write it down, right? Just the more you practice, the easier this is going to get. It's not going to come on the first day. You have to take a lot of time to practice. It's like when you're serving a tennis ball, you have to hit it over and over and over again. Okay, derivative means. Here are all the things we know a derivative means, right? The derivative is the slope or the rate of change. The derivative is the slope at a point. The derivative is the slope of the tangent line. The derivative is the instantaneous rate of change. These are all very easy functions that you did last week in your homework assignments, right? You had to find the derivative using those derivative definitions, plug in the numbers, do all that thing. Now you know the rules, so these problems are going to be a piece of cake, right? If I ask you to find the slope of this equation, y equals 1/4 x to the 4th minus x plus 2, add x equals 2, what are you going to do? Take the derivative and plug in 2. And now it's going to be super easy to take the derivative. The derivative is going to be, bring the power in front. 1/4 times 4 makes 1. X to the 3rd, subtract 1 from the power. Minus, what's the derivative of x? 1. And what's the derivative of 2? 0. So the derivative is x to the 3rd minus 1. The slope at x equals 2 is going to be 2 to the 3rd minus 1, 7. Okay, now it says slope of the tangent line, right? The equation of the tangent line to y equals 1/4 x to the 4th minus x plus 2 at x equals 2. Do you notice that this guy here is the same function as the one we just did there? Yeah, and you notice that the x values are the same? Yeah, so what do you already know about this tangent line? The slope is 7. Okay, the slope of my line is 7. I know my x value is 2. How do you find the equation of a line? You need a slope and a point. If you know that x is 2, how can you find the point? Plug into where? To the original function. 1/4 times 2 to the 4th minus 2 plus 2 is 4. So my point is going to be 2, 4. My slope is 7. My point is 2, 4. Equation of a line. Y minus y0 is m times x minus x0. Y minus 4 is m, 7, times x minus 2. Okay, this slope, I'm just going to put a line here so you remember that that's how I got that slope. Y minus 4 is 7x minus 14. Add 4 to both sides, 7x minus 10. What that means is if I graph this function, 1/4 x to the 4th minus x plus 2, and I graph this line, y equals 7x minus 10, then at x equals 2, they should be touching each other, and they should be going in exactly the same direction. Okay, if you graph your function and you graph your tangent line, then at the point x equals 2, the two things should be touching and they should be going in the same direction. What is the instantaneous rate of change? Instantaneous rate of change. Instantaneous means the derivative, right? At 3 seconds. So what do I need to do to this? Find the derivative and plug in 3. Okay, let's find the derivative. These are all just power rules again, right? This is a little bit harder because I have to do negative 4.9 times 2. What do you get when you do negative 4.9 times 2? 9.8, yep. And what's the power going to be now? 1, because 2 minus 1 makes 1. Okay, plus derivative of 40t, 40. Derivative of 6, 0. So plus 40. I was looking for the instantaneous rate of change at 3. So I'm going to plug 3 in for t. Negative 9.8 times 3 plus 40. Okay, 27. 29.4. 10.6. Someone should put that in their calculator. It's like my skill. I have to show it off, right? Computations in your head. There's this dude out there. What's his last name? Anyways, he's like a mathematician and he does like fast computations. He's really cool. You should look for him. I'll look up his name. I'll post a link for a video, you guys. Okay, we're gonna learn some. Yeah, let me scroll back up. I distracted you with the talk with the mathematician. It's Arthur somebody. I can't remember his last name. He teaches at Williams College.
I think I've seen that before.
You've seen it. He does like it's amazing what he can do. Like his super fast multiplications of like huge digit numbers. It's pretty cool. Okay, we're going to talk about, let's say, 2 more families of functions. We're going to talk about trig functions, sine, cosine, tangent, secant, cosecant, cotangent. And we're going to talk about exponentials and logs. So 2 more families of functions. We're going to talk about those functions and what their derivatives are. Okay, so you at the end of today are going to have this huge list of rules, right? We have a midterm on September 22nd, at which time you should know this huge list of rules. The best way to memorize a huge list of rules is to, every time you have to look it up, write it down. And then eventually you won't have to look it up anymore. Okay, so that's my tip of the day. Okay, here is a graph of sine x, and here is a graph of cosine x. What does the derivative tell you about a graph? The slope of the tangent line, yes? The slope of the tangent line. If I look at the graph of sine of x, where is the slope of the tangent line 0? At the tops and bottoms, right? So here at pi over 2, the slope is 0. Here at 3 pi over 2, the slope is 0. Here at negative pi over 2, the slope is 0. Yeah, agree? So what I'm going to do is I'm going to plot those points. I'm going to put them here. This green line that I'm drawing represents the slopes. Okay, here at x equals 0, right here at x equals 0, what would you say the slope is? What kind of number is it?
1.
Yeah, it's a positive number, about 1. Yeah, okay, at x equals 0, the slope turns out to be about 1. Okay, how about here at pi? What would you say the slope is at pi? Positive number or negative number? Negative number. Turns out to be about -1, yeah? How about at 2 pi? What's the slope at 2 pi?
1.
Yeah, back to 1 again. Okay, let's look at connecting these dots. This goes up, comes down, down, up, down. Does this green line look like some other function you know? Yeah, look at that. The green line looks like that one right there. The derivative of the sine function is cosine. I know, that's super cool. Well, that's because it's in a table, so it like gets shifted around when I draw on it. I don't know why that happens. Okay, I'm going to do the same thing for cosine. You might be thinking to yourself, I already know the answer. I don't know if you do or not, so let's see. Okay, let's look at the cosine graph. I'm going to ask you the same questions. I started with, where on the cosine graph do you think the slopes of the tangent lines are 0? X values. Can you give me X values? 0, right here at the tops and bottoms, right? The slopes are zeros at the tops and bottoms. So right here at x equals 0, I think that the slope of the tangent line is 0. Right here at x equals pi, I think that the slope of the tangent line is 0. Here at x equals 2 pi, I think that the slope of the tangent line is 0. So I'm going to put some zeros there. Here, here, and here. Okay. What do you think's happening at pi over 2? Has a negative slope of about 1, right? It looks like it's about a diagonal line, 45 degrees. A negative slope of about 1. So -1 down there. Oh, darn. It's not working as we wanted it to. Okay, how about at 3 pi over 2? What would you say the slope is at 3 pi over 2? About +1, yeah? And at pi over 2? Same, about +1. Okay, so this derivative looks like that. It has all the same zeros as sine, right? But what does it do? It might be hard to see because of the green on there, right? Yeah, it's going in the opposite direction, right? So this blue line and this red line for sine. So the blue line has all the same zeros, but this one goes down first when sine goes up first. How do you change direction? You put a negative in the front. Yeah, you put a negative in the front. So it turns out that the derivative of cosine is negative sine. Okay, I'm going to tell you the last 4, and we'll figure out how to get them later. We just don't know enough to be able to get them, but once we know them, we can use them. So Wednesday, we'll know enough to be able to get them. Right now, I'm just going to tell them to you. The derivative of tangent turns out to be secant squared of x. Remember that secant squared is an abusive notation. What that really means is secant of x all squared. Okay. So when I write secant squared, I'm sort of abusing notation. What it really means is secant of x all squared. If you need to write that down here, you can write that down. It's really that. So these two things are the same. When I write secant with the square here of x, what I really mean is find the secant and then square your answer. Okay, the derivative of secant is secant x tangent x. The derivative of cosecant is almost the same, but negative. Negative cosecant x cotangent x. And derivative of cotangent is negative cosecant squared of x. So the first two we could kind of see from the graphs. These all come when we get to the quotient rule, which is what we're going to do on Wednesday. Okay. Yeah, write that down. Okay, we're going to find the derivative of these functions. If I want to find the derivative of sine of x plus tangent of x, I can just find the derivative of sine and add the derivative of tangent, right? So look at your list. And what's the derivative of sine? Cosine plus, what's the derivative of tangent? Secant squared x. Easy peasy. Okay, if I want to find the derivative of 3 cotangent of x, I just do 3 times the derivative of cotangent. What's the derivative of cotangent? Negative cosecant squared. So the derivative of 3 cotangent is going to be negative 3, because of that negative, cosecant squared of x. Equation for the line should be of the line. That's fine. Okay, this one says find the equation of a line that's tangent to this function, pi plus 2 tangent of x at x equals pi. This is tricky because we're using tangent as a thing and then tangent as a function, and they're not really the same, right? So just be a little bit careful. Find the equation of a line that is tangent to this function, pi plus 2 tangent of x at x equals pi. How do you find the equation of a tangent line? Find the derivative to get the slope, yeah. And then how do you find your point? Plug in your x value. Okay, let's do that part first because that's easier. I'm going to find my point first. Y equals pi plus 2 tangent of pi. Pi plus tangent of pi is, no, there's no derivative there. I'm just doing tangent of pi. Tangent of pi is 0, so it's just going to be pi. Okay, so my point is going to be pi comma pi. That means my x value is pi and my y value is pi. Okay, I want to find the slope. To find the slope, I need to take the derivative. What's the derivative of pi? 0. It's just a constant, right? Pi is a constant. It's just some number, 3.1415. 265 3585. My 14-year-old can do like the first 100 digits of pi. It's kind of curious. I apologize. I am a nerd. Okay, derivative of pi is 0. 0 plus derivative of 2 tangent of x is 2 secant squared of x. To find the slope, I need to take the derivative at that point, pi. Yeah. So really this is 2 secant of pi squared. All right, what's the secant of pi? Who knows? Secant is 1 over cosine. Yeah. Cosine of pi is pi over here. Cosine of pi is -1. Yes, you need your calculator in radians to find that. Yep. So secant of pi is going to be -1. Squared is 1 times 2 is 2. So this should come out to be 2. Okay, so my point is pi pi. My slope is 2. To find the equation of a line, I'm going to do y minus pi, y1, is m2 times x minus pi. I can simplify this if we want to. Y minus pi is 2x minus 2 pi. Add pi to both sides. Y is 2x minus pi. Or you can leave it just like this. Y minus pi is 2 times x minus pi. I don't know. It just depends on whether infinity says y equals or whether it wants you to write the equation. You might have to be careful because your calculator might not have a secant button in it. You have to use the 1 over cosine button. So Desmos is great. You can just type in secant. It has all the buttons. Okay, so we did trig, and now we have exponentials and logs left. Those will be our last rules of the day, exponentials and logs. Okay, here is a graph of e to the x. I don't know why it has f of x there twice, but here is a graph of e to the x. What do you notice about e to the x? It's exponential. It's always going up. Yeah, so the slopes are always positive. So my derivative function should always be above the x-axis, positive, yeah. What kind of number is the slope here? Kind of small, really close to 0, right? It turns out it's not ever actually 0 because this doesn't ever get horizontal exactly, but kind of small, really close to 0. What's happening to the slopes as I move to the right? They're getting bigger and bigger and bigger. Okay, so over here, we think that the slope is really close to 0. Over here, we think the slope is really close to kind of like 1, right? Kind of like 1 right there. Over here, we think this slope is a bigger positive number, kind of like 2 or 3. Yeah? What happens if I connect these dots? How do these two functions compare? They look the same. The derivative of e to the x is e to the x. He's the best function ever.
Wouldn't be x minus 1 then, so it'd be like,
No, because it's not the power rule. And if to have the power rule, you need x to be the base. If x is not the base, then you can't use the power rule. If x is in the exponent, you got to use new rules. Okay, what do we do if the value, if the base of my exponential is not an e? Well, we put in a natural log here. So we say a to the x natural log of a. It comes from the fact that a to the x is the same as, you can rewrite it with an e in there instead. E to the, I'm gonna put natural log in there. Well, it comes from that fact. I have to think about that for a second. So this guy happens when your base is not e, like if your base is 2 or 7. Remember, an exponential function has to have a positive base. It can't have a negative base.
I'm confused with this.
ln, that's the natural log.
Oh,
Yeah. Okay, let's talk about natural log of x. Who knows what the graph of natural log of x looks like? What does the graph of natural log of x look like? Kind of like e to the x.
let's start like a negative row.
It starts here at the negatives and goes like, it has a vertical asymptote at x equals 0. Remember, e to the x and natural log of x are inverses of one another. So this guy has a vertical asymptote at x equals 0. Okay, let's try to graph his derivative. What kind of number is the slope right here? A really big positive number, right? A really big positive number, okay? What kind of number is the slope right here? Like a medium number, like 1, right? And then over here, what kind of number is the slope over here? Small, getting close to 0, yeah? So it looks like this. This is the graph of 1 over x, if you don't know that. So the derivative of natural log of x is 1 over x. Natural log is log base e. So again, we have to talk about what happens if your base is not e. What happens if you're going to do log base a? Well, we just stick in that natural log again. So the derivative of log base a of x is 1 over x natural log of a. So just always remember, when your base is not e, stick in a natural log of your base. Okay, we're gonna practice. And notice that I'm gonna mix rules together, right? Let me make sure everybody can write them down. I'm gonna mix rules together. Some of these are exponentials and some of these are polynomials. So some of these are gonna use the power rule and some of these are gonna use the new rules. So for instance, in this first problem, this first term is an exponential because the variable x is in the exponent. The second term, what rule am I going to use on that one? Power rule, because his x to a power. All right, third term? Exponential. Yep, he's going to be an exponential with an natural. Fourth term? Zero. There's no x's there, right? He's a constant term. 0, no x's, constant term. Okay, this guy's a natural log. I'm going to use this natural log rule. How about this guy? Power rule. I'm going to rewrite him and use the power rule. And then this guy? 0. Okay, let's try it. I'm going to do this one first because I'm just going to do the rewriting part. How do I rewrite 3 divided by x? 3x negative 1. Okay, great. Okay, now I'm going to take the derivative. Derivative of 3e to the x is 3e to the x plus the derivative of x squared is bring the power in front, 2x to the 2 minus 1 makes 1. So I'm not even going to write the 1 there. Okay, plus derivative of 2 to the x. 2 to the x is this rule here, where my a is 2. Yeah, anytime my base is not just e, I have to use this rule here, where my a is that base. So that's the rule with my a to be 2. So 2 to the x, natural log of 2. Minus, what did you tell me the derivative of e is? 0. Okay. Good. All right, next one. Y prime. Derivative of natural log of x? 1 over x. Plus, in this guy, I'm going to bring the power in front. So 3 times negative 1 makes negative 3 x to the negative 2 plus 0, right? So I can leave that out. There's more. I thought we were done. We're not done. It's never going to end. Oh, no, we're done. We're done. I'm going to post this for you. This Desmos activity, I'll post it in the D2L. It's just a whole bunch of practice problems so that you can just practice using this derivative rule. Here's what I'm here to tell you today. On Wednesday, we're going to talk about the product rule and the quotient rule. Okay, you need to be proficient at these rules we did today. Because if you're not proficient at those rules, when I mix them inside some other rules, your mind is just going to be blown. So you need to spend some time before Wednesday, which maybe you don't normally do, either working on infinity problems, the ones on this list, or practicing this Desmos thing. Because Wednesday, when we use the product rule and quotient rule, if you haven't practiced at all, we're going to go way too fast. Okay, so that's your goal. It's quiz day. 2 quizzes due today, and then practice for Wednesday. See you then.